Hello, so this is the introduction to virtual memory for ECE 3058, and this just briefly goes over some concepts which you'll go more in depth into in class, but this should help you some of the concepts needed for the lab. Why do we have virtual memory? So it's due to the difference between the view of memory from the hardware and the software. So we have this hardware view of memory where maybe we have two different memory modules, 4 gigabytes each, that combine for a total of 8 gigabytes of memory. So this is the physical memory of your computer, the memory it definitely has. But if you're looking at it from the programmer's point of view or from the software's point of view, you have this massive amount of memory. So let's say we have a 64-bit address space. We have 2 to the 64th, which is way larger than the 0 to 8 gigabytes that needs to be indexed in physical memory, right? So the programmer's view is saying, oh, we have way more memory than what we actually do have to access in hardware. So from the programmer's point of view, maybe the top of this is the system, so space stored for the system. Maybe the portion of this is the code, so the instructions that you're going to run for this program. Maybe some statically allocated data. And then, of course, we have the heap, which is super important. So a lot of you have programmed in C or C++. This is where when you're using malloc or calloc, or for C++, new or delete. Or delete to remove. This is where you're allocating memory. And then usually at a very high memory address in your program, you have the stack as well. And if I'm a programmer, I don't really want to worry about the difference in where the stack and the heap is. I just want to imagine that I have an infinite amount of memory and that I can access anything and run anything. So that's how the programmer wants to view it, right? And also what we have is we may have many programs running at once. So every program wants to look at their own thing and consider their own thing. So like, let's see, maybe the code are held in the same memory address for that program in the programmer's point of view memory, which you obviously couldn't have in the hardware's view of memory. Pretty much the purpose of virtual memory is to kind of reconcile these two different views of memory, so the programmer and the software can view it on its own, and everything will still work smoothly in the hardware. So to do this, we need to map our virtual memory to physical memory, right? So what we have is we have our virtual memory here, and our virtual memory has these things called pages, which is where we can insert the memory for the program, right? A generic size of a page is about 4 kilobytes. So you can see here on the left that it goes page 0 is 0 to 4 kilobytes, then page 1 is 4 to 8 kilobytes, etc., etc. And the memory is similarly segmented. Well, not physically, but we can imagine it's physically segmented, right? And the physical memory kind of does the same thing, except in physical memory it's called a frame. So important difference, virtual memory has pages, physical memory has frames. So we need some way of mapping these pages from the program to physical areas in memory. So maybe we want page 0 to go to frame 0, page 1 to go to frame 3, and page 2 to go to frame 4. And now let's say we have a different program running at the same time, right? Maybe we have the separate program on the right here, and it also has its page 0 through page whatever. Obviously, there's not enough space here. There's generally more than 32 kilobytes or 36 kilobytes of data in of memory. But so here we might have page 0 go to frame 1, page 1 go to frame 2. And this is actually kind of interesting. So what if page 1 of the initial program, which we can see is pointing to frame 3, wants to access the same memory as our second program here on the right. Maybe page 2 goes to frame 3. And then let's say if page 1, or if you're writing something from the first program that writes to its page 1, that actually writes to the physical address in frame 3. So now if the second program reads from that later, from using its page 2, you need to be aware that it's been written to, and it will actually see what the first program wrote. So you're going to learn a little bit more about this in class. And if you take an operating systems course later on, you'll learn about a ton of techniques that may affect this. But that's beyond the scope of this short video. So yeah, so now we need to know a way. How do we know where to map everything? How do I know page 0 goes to frame 0 from the first program, or page 1 goes to frame 3? So what I have is I have page tables. So each of these has their own page table, and the page table is kind of controlled by the OS. So everything's here is controlled by the operating system. So the programmer does not need to worry about this. Let's go into how the page table works and how we get address translation. So let's say I'm doing a load to some address, right? The load you're doing when you're programming is the virtual address. And the virtual address can be split into two things. So the virtual page number and the page offset. So here you can see the page offset is 12 bits, and that's just because we're considering 4 kilobytes pages. So to index into that, it's 12 index bits because 2 to the 12th, right? So very similar to some of the math we did with caching. Either way, so now the remaining bits of our 32-bit address are the virtual page number. And we use this to index into our page table, which is shown in yellow here. So let's say the virtual page number, it goes and looks, it checks the valid bit in the page table base register. And if it's 0, this means it's a page fault, right? This means the memory you're looking for isn't there. But now let's say it is there, the valid bit's 1. Then we get the physical page number from our page table. We pull that physical page number out, and we use the same page offset that we had from before, combine them, and that's going to be our physical address, which we're actually going to use to access memory. And we're going to use that physical page address, go to that address, and that's going to give us the actual result. Here we have an example. So if you would like to pause it and take an attempt at this before I go through it, I'll give you a couple seconds after explaining the question. So just assuming 4 kilobyte pages, we have the page table here shown and the virtual address in hexadecimal 0xF643C18A. You need to find what the physical address is. So I'll give you a second now to pause it if you would like to attempt this on your own. Okay, so I'm going to start going over it. Or the first thing we have to do is we need to split up our virtual address, right? So how we do this is we find the page offset first, because that's the amount of page offset bits determines what the page offset is, and then the remaining bits of the virtual address we know are the virtual page number, and that's what we're going to use to index into the page table. We do say we assume 4 kilobyte pages, so same as before, because 2 to the 12th becomes 2 to the 12th indexes into 4 kilobytes. We know that we have 12 offset bits. Using that, we know the page offset is the last 12 bits, which are right here, 18A, because it's in hexadecimal, which means our remaining virtual page number is F643C. So we have the least significant 12 bits of the offset, and then the remaining bits are the virtual page number. So now we need to use this virtual page number to index into our page table. And in this page table, we can find the physical page number. This virtual page number is 0xF643C, which goes right there. So now we know that 1844C is our physical page number. So now we need to combine this, because this isn't our final physical address that we're looking for. We take the physical page number and we combine it with the page offset. So the page offset, 0x18A, the exact same as the one from our virtual address. We don't need to do any modifications to this. We just take it straight as is. Then we combine these two. So our physical address now becomes 0x1844C 18A. And using that, that's the physical address. And that's a very basic example of how this would work. In class, you may learn about TLBs and a ton of other techniques we use to make this system faster. This is obviously very integral to computers, so tons of optimizations have been made, even more than what we can cover in this class. So yeah, if you guys have any questions on these topics, feel free to ask on Piazza or come to any of the TA's office hours. And I'd suggest, as always, getting started on the lab early. So good luck, everyone.